Greetings, good morning, good afternoon, good evening, whenever you're watching this. This is the first PowerPoint voiceover for Chapter 6. We're going to be doing 4 sections in Chapter 6, 6.2, 6.3, 6.5, and 6.6. So, starting off with Section 6.2, at the very top here, you see the link to my YouTube channel. You may, obviously you have this already, but if you haven't, lost it, there it is. So normal curves and sampling distributions. Just to begin this, in the previous sections, right, we used what's called discrete random variables. As we move into chapter 6, we're going to be using something called continuous random variables. By discrete, I mean numbers that take on a finite value, counting numbers. We talked about the number of boys or girls, the number of marbles in a bag. We talked about the number of ways that you can get a 4 when you roll a couple of pairs of die. Key thing here is the answers were all whole numbers. We're going to move now to numbers that could take on decimal representations, continuous random variables. What this is going to necessitate is drawing what's called a normal curve. Whenever you're doing these problems, you've got to be drawing this curve. You're going to be finding the areas under curves and then eventually finding X and Z values. So right now, this is just some basic definitions. A discrete random variable can take on only a finite number of values. A continuous random variable can take on a countless number of values. We're going to be working with continuous random variables. The distinction between discrete and continuous is important because the different mathematical techniques associated with the two kinds. For instance, the number of eggs that a hen lays. Well, a hen's not going to lay 2.343115 eggs. It's going to lay either 0, 1, or 2. Those are the possible values. If I count the number of students in our statistics class, it's not going to be 3.2 or 20.5. It's going to be 21, 22, and so forth. The amount of milk that a hen lays, sorry, amount of milk that a cow produces. All right, that's not, chances are going to be exactly 1 pint or 1 quart. It's going to be something that um, is over a continuous span. In other words, it could be 6.3 gallons. I'm not even sure how much milk a cow produces, but it's not going to be, chances are it's not going to be an exact whole number, continuous random variable. All right, here again, same idea, discrete numbers that have values like 0, 1, 2, or 3, things we did back in chapter 5, chapter 4, and so forth. And now we're working with values that are continuous random variables, things that could be on a continuous scale. Simply means that chances are they're going to be decimals. All right, so this counter kind of points it out. All right, you're counting with a counter, you have whole numbers. All right, 0, 1, 2, 3, whatever. Measuring electricity, it could be anything from 0 to 9, could conceivably obviously be some sort of a decimal. Continuous versus discrete. All right, so here's this chart. This is not a chart, it's actually a curve. It's a normal distribution. All right, the bell curve. What is so important here is that how can I take a area under a curve and associate it with probability? Well, what's neat about this is the area under this curve is exactly 1, and we know that the sum of the probabilities of all the outcomes in a sample space and probability is exactly 1. All right, so the area under the curve. This is how we can use this curve to calculate probabilities. Now, what's interesting is we start out with what's called a standard normal. Standard normal is neat because the mean always is 0 and the standard deviation is 1. This is sort of like Alice in Wonderland. There's not many data sets where your mean happens to be exactly 0 and your standard deviation is 1. But we're going to see as we move on in chapter 6, we're going to take things that are non-standard, and by using what's called z-scores, we're going to standardize them. And when we standardize them, we can use our tables and our charts. And our calculator is going to play a big part in to do this, but we still need to draw this curve each and every time we do a problem. So you're going to get pretty familiar with drawing this bell curve. Next thing I want to point out here is that way to the left, as far as I can go to the left, is negative infinity. As far as I can go to the right is positive infinity. We're going to see on the calculator, negative infinity is a negative E99 and a positive infinity is a positive E99. We're going to need to tell the calculator if we're going all the way to the left or all the way to the right. There is no key for infinity. We're going to use either negative or positive E99. Standard normal distribution. All right. Once again, check this video out. I can't play it I can't play a video within a video. But when you download PowerPoint 6.2, please watch this video. It says here, clearly explained, right? Normal distribution, standard normal. People often ask me, well, how do I know that the area under the curve is exactly 1? Well, there's this formula over here, right? It's a function. You have e raised to the negative 1h. You're not going to have to memorize this formula with the denominator. Pi times the square, I'm sorry, sigma times the square root of 2 pi. Watch this video. It actually proves that, yes, we are correct, that the area under this curve is 1. Sometimes we take things for granted and we never question anything. But this video explains, hey, how I can equate the area under a normal curve to probability because the area is exactly 1. Check out that video. Things that are normally distributed, heights of 3-year-old females, all right? And as you can see here, this distribution, it's pretty darn close. If you look down bottom, it's not exactly a normal bell curve, but pretty darn close. All right, I'm taking these values. It starts out with very few values that are low. It reaches a crescendo, a high value, and then it tails off. All right, a normal curve. This video talks about skewness, things that are left skewed and things that are right skewed. Here again, we're working with a bell curve, which is symmetric, left and right, right skewed and left skewed. Here again, you can check out this video to get a deeper understanding of what we're talking about here. Once again, I can't play it out, or I can't play a video within a video, but when you play your PowerPoint, you can see it there. Hopefully you're using the latest version of Office with the latest version of PowerPoint. Of course, you realize you can download this from the MasterSwave site. All right, incomes. All right, it's a right skewed. Very few people making 150, 180. And you got a couple of people out here making between, well, not a couple, but making some huge amount of dollars here, right? Right skewed. Right, heights of students, this is left skewed. Just examples of things that are not bell shaped, they're skewed either left or right. Suppose this is exactly what the video talks about when I call him Big Al, when he introduces Z-scores. Suppose Tina and Jack are in 2 different sections of the same course. Each section is quite large, and the scores on the midterm exams of each section follow a normal distribution. In Tina's section, the average mean was 64, her score was 74. In Jack's section, the mean was 72, his score was 82. Both Tina and Jack were pleased with their scores. Each was 10 points above the average. However, the fact that each was 10 points above the average doesn't really tell us how each did with respect to the students in their sections. All right, here's a graph of Jack's scores. Here's the mean. Here's Jack's scores. Now notice Tina's scores. The bell curve here is more compressed. It's more compact. All right, here's the mean, 64. Here's her score, 74. All right. The preceding situation demonstrates that it's not sufficient to know the difference between a measurement and the mean of it. We need to consider the spread of the curve. Notice these scores are more compact. We're here. What this is indicating is that the standard deviation is greater. The curve is fatter, so to speak, where this curve here is narrower. Standard deviation of scores don't vary as much as they did in scores in Tina's class don't vary as much as they did in Jack's So to standardize scores, we take a raw score and we standardize it by finding how many standard deviations that score is away from the mean. It's called a z-score. And to calculate it, you take an x-score, you subtract the mean, you divide it by the standard deviation. All right, what we're doing here, we're finding out how many standard deviations the score is away from the mean. It's called a z-score. Now, there'll be times when you're going to have to calculate this pencil and paper, and I'll get into that. Calculator is going to bail us out a lot, but it's not going to do everything for us. There's times we need to know the math. Here's the same formula again as z-score is your x-score minus the mean divided by the standard deviation. It gives us the number of standard deviations. What happens is that we're going to see problems that have all different means and all kinds of standard deviations. Right now, it's all going to be 0 and 1, but as we move forward, and we can't have charts for every combination. So how we get around that is we standardize them by using a z-score. All right. A standardized score or z-score of a measurement tells us the number of standard deviations the measurement is away from the mean. All right, so we see here that in Jack's section, all right, his score was 1 standard deviation away, and Tina's score was 2 standard deviations. She was 2 standard deviations above the mean. Jack was only 1 standard deviation. Now, obviously, Jack did better. He did an 82, and Tina had a 74. All right, but the idea is relative to her whole class, Tina did better. Her score was 2 standard deviations above the mean. Jack was only 1. But you're saying to yourself, hey, great that she's 2 standard deviations. I would rather have an 82 on a test rather than a 74. So relative to her class, she did better, but Jack's score obviously still was higher. All right, this is how you calculate a z-score. You take the raw score, subtract the mean, and you divide it by the standard deviation. Notice in Tina's class, standard deviation was 5. In Jack's class, it's more spread out. His standard deviation was 10. You see, when I haven't done this recently, but I may do it. I'll give you the standard deviation of your test scores. Right, a low standard deviation means scores were closer to the average of the entire class versus a higher standard deviation means that scores were all over the place. There's some extremely high scores and then you have some extremely low scores. On probability, standard deviation was rather small. Most of the folks did really well. All right. Heights and weights are measured on different scales with different units of measure. You measure height in inches, you measure weight in pounds. So here's a case here. We want to know which is more extreme, somebody that is 76.2 inches tall or somebody that weighs 237 pounds. So what we do, we take each of these scores and we standardize it. We find the z-score, how far away were these scores away from the mean. So we see that a height of 76.2, if I take the score and I subtract the mean of all men, I divide it by the standard deviation of all men, I have a z-score of 2.60. And if I do it with the weight, doing the same thing, taking the weight of 237, subtracting the mean of all men, dividing by the standard deviation of all men, the z-score is only 2.45. So what happens is somebody that's 76.2 inches tall, it's more extreme because the z-score is a larger number. Things that have z-scores that are bigger than 2 or smaller than -2 are called unusual values. Ordinary values lie between -2 and +2 standard deviations away. So sometimes when you want to compare different measurements, you standardize it by calculating the z-score. All right, standard normal. We get into it now. It'd be a futile task to try to set up a table under the normal curve for each different combination of mu and sigma. Right now, as I said before, we're going to be working with means of 0 and standard deviations of 1. As soon as we move to section 6.3, that's going to change. Now, I can't have a table. Right? My calculator can do it, but sometimes we have to use the table. I can't have a table for every combination of means and standard deviations. So we standardize these by making calculating z-scores. Now, here's what's really unique about a standard normal. Standard normal has a mean of 0 and a standard deviation of 1. Kind of Alice in Wonderland because not many data sets have this situation. But what's unique about this is if I calculate a z-score for a standard normal, I take the raw score, I subtract the mean, and I divide it by the standard deviation. What ends up happening is the z-score and the x-score are synonymous. That simply means is when I have a standard normal, my x and z-score, there's no standardization needed. My z and my x score are one and the same, all right, because of the fact the mean is 0 and standard deviation is 1, which makes life a lot easier. Notice here I got negative infinity and positive infinity to the negative infinity to the left, positive infinity to the right. When your x score is equal to your mean, your z score is 0. If your x score is to the right of the mean, your z score is going to be positive. If your x score is to the left of the mean, your z score is going to be negative. To the left of 0, negative. To the right of 0, positive. Your table. Now, the very first thing that I ask you to do in the homework assignment is to download this little table, your z-scores, positive and negative z-scores. The table is only designed for standard normal. It's on 2 pages, one positive, one negative. All right, each value in the body of the table is cumulative from left to right. This is the table here. You start off with the left column and you coordinate it with the right column. For instance, if I'm looking for 1.63, well, I see the 1.6 here. I see the 0.03 there. So I'm looking at a value of 0.984. What really gets kind of messy is down the road, we're going to have to look in the body of the table and take a value, let's say a value of 8.925, and say, hey, that's the same thing as 1.24. So it works both ways. Right? We do this left column followed by the right column. As a matter of fact, in the video, he kind of walks you through this. He does walk you through this. All right, so that was a positive. These are the negatives, these scores. Now notice there's a couple of values down bottom, halfway between 0.0505 and 0.0495. It gives us the exact z-scores here. It's the same thing here, halfway between 0.0051 and 0.0049. It tells me that that z-score is a negative 2.575. All right, first example. The Precision Instrument Company manufactures thermometers that are supposed to give a reading of 0 degrees centigrade at freezing point of water. Tests on large samples of these instruments reveal the freezing point of water. Some thermometers give a reading below 0 degrees, denoted by negative numbers. Some give a reading above. This is all well and good, but this is just setting up the problem. The problem really starts here. This is the meat of it here. He says, hey, assume that the mean reading is 0 degrees centigrade, standard deviation is 1. The minute I see that, mean of 0, standard deviation of 1, I got a standard normal. All right. Also, assume that the readings are normally distributed. If one thermometer is randomly selected, find the probability that at the freezing point of water, the reading is less than 1.27. All right, so this is what we're looking for. We're looking for the probability that at the freezing point of water, the thermometer is reading less than 1.27. All right, so the first thing I do before I do anything else is I draw my bell curve. Right here, the high point is the mean. I've marked that as 0 because he tells me mean is 0. All right, this is 0. Obviously, 1.27 is a positive number. It's to the right of 0. So I draw a vertical line. Now, what am I looking for? Probability that my z-score is less than that. Well, less than 1.27 is the area from this vertical line to the left. All right, your tables are always left-handed tables. The value that we're given in the table is always to the left of your z-score. So I'm looking for the area that's shaded in green right here, right to the left. All right, so if I go to my table, all right, initially, which we won't have to do because our calculator is going to help us out, I'm looking for the z-score that corresponds to, the area that corresponds to 1.27. Now 1.27 is 1.2 plus 0.7. I'm finding the 1.2 along the left-hand edge and the 0.07 across the top. And where they intersect, I'm reading 0.8980. You won't always have to do this, but there'll be times when you're going to. The reason you're going to have to do this is that when we move forward to sections 6.2 and 6, when we move to 6.3 and 6.5, 6.4 and 6.5, 6.4, 6.5, you're going to get discrepancies. In other words, your calculator is going to be almost a little bit too precise. See, the answers on the exams are going to be done pencil and paper, so you're going to see discrepancies. And many times, to get the exact number, you're going to have to rely on the table. So even though your calculator helps you out big time, it's still you need to know how to use the table. So that's how you find the area associated to the left of 1.27. That's where these two guys intersect. All right. So from the table, he says, hey, the area from this vertical line to the left is 0.8980. So the probability, because the area under the whole curve is 1, I can relate it to probability. The probability of randomly selecting a thermometer or a reading less than 1.27 degrees is pretty high. It's 0.8980. All right, that's the exact same slide. No difference there. Okay, how can my calculator find this answer? All right, so this video here shows you the discrepancies, because some folks, I don't know how many, have an 83 or an 84 that behaves like an 83. So watch this video because, especially if you have the 83, it shows you the difference. Just like there was a difference when we were in chapter 5 with binomial probability distribution and binomial cumulative. The 83 doesn't walk you through it like the 84 does. You have to put the values in the correct order, separated with a comma. All right, so here's an example of using the 84. I'm looking for the probability of a reading on a thermometer being less than 1.27. So here's my 0, here's my 1.27. I draw a vertical line. I'm interested in the area to the left. My table is always set up for the area to the left. Now I'm going all the way to the left as far as I can go. That's negative infinity. But for calculator purposes, that's a negative E99. You put this in, your calculator will put the -1. You don't have to put that in. You put that negative sign, that white key, followed by a second function comma. It actually puts the 1 in there for you. The upper limit is 1.27, mean of 0, standard deviation of 1. All right, and I actually do that for you here. Here again, I can't show it to you because I can't show a video within a video. But when you're going through the PowerPoint, this is great to watch this, to watch my explanations. But in addition to watching the video, you got to open up the PowerPoint and go through the slides, especially how to see how to do these. All right, so we start out going to the left. And as you would imagine, now sometimes we need to go to the right. Here's a case here. We're looking for the probability of the thermometer reading bigger than Z greater than 1.23. Well, here's my 0. Here's negative 1.23. It's obviously to the left because it's a negative number. All right, so I'm looking for the area to the right greater than this. All right, so here's the deal. Your table is a left-handed table. If I went to my table and I looked up a z-score of negative 1.23, it would give me the area from this vertical line to the left, but that's not what I'm looking for. I want the area on the other side. So once I calculated this to be 1.93, if I was using my table, I would have to subtract that from 1 to find the area to the right, which is what I'm looking for here. All right, the left-handed table, the area that's associated with that value, negative 1.23, is to the left, but that's not what you're looking for. You want the area to the right. So once you found that, if you were using your table, you'd have to subtract from 1. But your calculator comes to the rescue. Here again, we get an answer here, 0.8907, subtracting the area associated with that value from 1, giving us 0.8907. All right, there it is. Negative 1 point. There's the negative 1.2. There's the 0.03 where they intersect. That's how I got that answer of 0.1093. All right, here again, your calculator bails you out big time. All you need to do is put the lower bound, the upper bound, the mean zero standard deviation. But don't discount using the table. It's still going to be, in some cases, it's going to be mandatory that you do it. All right, so we went to the left, we went to the right, and the third situation is, hey, what if I want the area between, in the middle, so to speak? Here's a case where I want the probability that the reading on the thermometer falls between -2 and 1.5, between -2 and 1.5. Now, once again, the top part here, the highest point on the graph on the bell curve is 0. So -2 is to the left, 1.5 is to the right. If I went to my table, all right, and I found a area associated with 1.5, it'd be from here all the way to the left. If I went to my table, I found an area associated with -2, it'd be from here all the way to the left. And then I would subtract. If I wanted the area in green, I'd have to subtract the two. All right, so it takes some time. We're finding the area in between. But as the next slide is going to show, your calculator is going to bail you out. This is the lower limit. This is the upper limit. Mean is 0. Standard deviation is 1. All right. So here's a case that 91.4% of the thermometers had a reading between -2 and 1.5. This shows you how to get around that with using the calculator. Once again, I can't play it out of this video. You need to play it out of the PowerPoint. Kind of helps you out. Area to the left, area to the right. An alternative approach to finding the area in between. All right, got a handy slide to print out. All right, some actual examples. All right, he's looking for the area, less the area. Probability that your z-score is less than 0.75. The area in green. And here we're looking for the area to the right. Here, the area in between. In between. All right, so I do each and every one of those for you on the calculator. All right. And here are the problems actually done out pencil and paper. But initially, for standard normal, you're always going to try to use your calculator. The only time you're going to revert back to maybe using a table is if there's a huge discrepancy between what your calculator gives you and the answers that are presented to you on quiz or test. All right. As is the case in many instances in mathematics, we start one way, then we flip the script, come back the other way. Right now, I'm giving you a x, which is the same as the z-score. I'm looking for an area. We flip the script. I give you the area, then I want the x or the z-score. It's called inverse norm. All right. Here's a case where, before I gave you a z-score, you gave me the area, which equated to probability. But what if I give you the area and I want the z-score? We're fortunate here with standard normals that z and x are one and the same. Here again, I'm looking for the 95th percentile. Now, if you score in the 95th percentile, you did better than 95% of anybody else. The area that's associated with this z-score is from this line to the left. Well, we know that's 0.95, all right, 0.95. Now, if I went to the body of the table and I looked up 0.9500, the closest value that I would find with that is 1.645. We're flipping the script. Instead of me giving you the z, you giving me the area. I now give you the area, you give me the z, which in a standard normal is the same as an x score. It's always going to be that way. All right, that one's going to come out a little better. I thought I had changed that should have been a better image of the z scores. Let me just go back for a second. Yeah, that should have shown up. That should have given me previous. That should have given me the area of 0.95. That's what should have happened here. I should have found 0.95 here. It would have given me that z-score. I apologize about that. That's all right. Here's a case where we're looking for these two z-scores. The area from here to the left is 0.025. If I went to my chart in the body of my table, looked up the closest value I could find to 0.025, I would have gotten negative 1.96. Now, what's interesting about this bell curve, it's symmetric. If this area here is 0.025 and that's 0.025, notice negative 1.96, this guy here would be a positive 0.96. Now, to find that, if this little bit of area here is 0.025, from here to the left is 0.9750. Go to your body of your table, look up 0.9750, and you'll find this to be a positive 1.96. It's symmetric. Sometimes you can make use of that. All right, there it is, negative 1 point. And there's a negative 1.9. There's the 0.06. Do you see it? 0.025. Don't always have to use the table, but you can't sleep on it because there'll be times when you have to do it. Show me how the TI can make this easier. Well, here's the inverse norm. You go to second function bars, you come down to number 3, I believe it is, inverse norm. Now, the inverse norm wants 3 inputs. It wants the area, the mean, and the standard deviation. All right. On the 84, it walks you through that. It says, hey, area, mean, standard deviation. On the 83, it goes inverse norm, and then it relies on you to tell it. Well, once again, I'm telling you, the inverse norm function wants the area first, the mean second, and the standard deviation third. All right, and there's my answer. All right, I'll find that to be negative 1.96. Now, to find that, I'd have to tell my calculator, hey, the area that's associated with this number, which I didn't know, is from here to the left. If that little guy there is 0.025, the area from here to the left is 1 minus 0.025. It's a complement rule all over again. Right? Don't fall for it. You just can't put in 0.025 and expect it to give you an answer of 1.96. No, it's a left-handed table. He talks about some tables being center. Ours is a left hand. The area that's associated with that number is from here to the left. And that's what it is, 0.9750. That's why I'm using inverse norm. Flip the script. Once again, here I would enter in point 9798. Here I would enter in 0.2546. Now, notice here, I'm looking for this z-score. The area that's associated with that z-score is from this vertical line to the left. Well, he tells you that's the area here. This little piece here is 0.1075. Big deal. I need to know the area to the left so I can input it into my calculator. Well, the total area on the curve is 1. So if that little guy there is 0.1075, this area here, which I'm interested in, is 1 minus that. That's what I would enter into my calculator. Don't fall for it and just enter that number and go, gee, I got it wrong. Same idea here. To find this z-score, I need to know the area from this vertical line to the left. All right, so if this guy, all this area is 0.9418, the area that I'm looking for, or I need to input into my calculator, is 1 minus that 0.0582. And here all I'm showing you is if you were doing a pencil and paper, that's what it would look like. Your calculator will do those if you want to try those two. All right, so it's a lot going on here. The most important part is you've got to be drawing these bell curves. If you don't draw a bell curve for each problem, you're setting yourself up for failure. Drawing the curve is no big deal. We got to be thinking about, hey, where am I going? Am I going to my right? Am I going to my left? You got to know about negative and positive, E99, a few other things. So there's a lot to this. Yes,